So here we're looking at the retinal structure again, but this time I want to kind of emphasize a mechanism that occurs both in bacteriorhodopsin and halorhodopsin. This is a mechanism that is important because it shows a proton coming out, and that is very important when it comes to chloride chloride coming in as well. So what we have here is we have the photoisomerization of retinal, which is a key event, like we said. So when retinal is in its excited state, the retinal is positioned so that it can transfer a proton to the threonine, 85 here, the side chain, which is positioned actually on the extracellular side of the protein. The threonine 85 then quickly hands off that proton to the extracellular space, and this is done in a mechanism similar to a fighter-fighter's bucket brigade, as the water molecules along the extracellular space help carry this proton away. So now the negatively charged retinal takes another proton from the histidine 95, and this one is actually positioned toward the cytosolic side of the protein. And the retinal then returns to its ground state, and that cycle repeats again. And now the cycle is important because, again, it releases a hydrogen proton, and having that proton out gives that proton motive force that is helped to power ATPase and bacteriorhodopsin, but also in halorhodopsin will come into play when it comes to chlorine binding.